Hello everyone, myself Siddharth and you are watching Indian Mathematical class. In today's lecture, first we will see some theorems and after that we will discuss the difference between limit and the limit point of the sequence, and at the end of the lecture we will quickly have a look at some results. So let us start our lecture. Theorem: every convergent sequence is bounded. Proof: let A and be a convergent sequence converging to L, and I have taken the value of epsilon equal to 1. There exists a positive integer m such that mod of an minus L less than 1 for every n greater than or equal to m. I have just applied the definition of the convergent sequence, and here value of the epsilon is 1. Now I am opening this mode. So it will give me this inequality, and I have just added this value L, so which implies that L minus 1 less than an less than L plus 1 for all n greater than or equal to m. Let small k equal to minimum of a1 a2 up to am minus 1 and L minus 1, and I am taking capital K is equal to maximum of a1 a2 up to am minus 1 and L plus 1. So every term of the sequence will be between these two, small k and capital K, for all n belongs to n. Therefore, which implies that the sequence an is bounded sequence. Okay. Here every term of the sequence you can see here is between these two real numbers. So this sequence has become bounded. Note 1. The converse of the above theorem is not true. That is, a bounded sequence is not necessarily convergent. For example, consider the sequence n is equal to minus 1 power n. Clearly this sequence is bounded because the GLB of the sequence is minus 1 and the least upper bound of the sequence is 1, but the sequence is not convergent. So we can see here that a sequence, if it is convergent, then it will be bounded, but a bounded sequence, second note, boundedness is a necessary condition for the convergence of the sequence. But if the sequence is not bounded, then it will not be convergent. For example, consider this sequence. We know that this sequence is not convergent because it is unbounded. Next result: if the sequence an converges to L, then the sequence mod n converges to mod L. Next, if a sequence n diverges to infinity, then n is bounded below but unbounded above. You can consider the sequence n here. Okay, it is bounded below. 1 is the lower limit of the sequence. Okay, the lower bound of the sequence is 1, but the sequence n is unbounded above. Next, if a sequence n diverges to minus infinity, then an is bounded above but unbounded below. Here you can consider the sequence minus n, and we know that minus 1 is the upper bound of the sequence and the lower bound of the sequence does not exist, and we know that minus n, the sequence is unbounded below. Note, the converses of the above two theorems are not true. That is, if the sequence is unbounded above, I cannot say that it will diverge to infinity. And also, if the sequence is bounded below, I cannot say that the sequence will diverge to minus infinity. Let us understand this by an example. Consider the sequence n where n is equal to n if n is even and 1 upon n if n is odd. You can see here a graphical presentation of this sequence. If I put here 1, it will give me 1 for 2, the next term is here. If I put here 3, then it will give me 1 upon 3, and if I put 4, it will give me 4, 5, it will give me 1 upon 5, and for 6, the term will be 6. You can see here that the even terms of the sequence are approaching to infinity, and the odd terms of the sequence are approaching to 0. And we have discussed in our previous lecture, if the sequence diverges to infinity, then limit of its even terms and limit of its odd terms both are infinity. Then only I can say that the sequence diverges to plus infinity. But here in this case, I can see here that the limit of its odd term is 0 and limit of its even term is infinity. So the sequence is not divergent and it does not diverge to infinity, but the sequence is unbounded above and bounded below. The next example is, consider the sequence an like this: minus n if n is even, minus 1 upon n is if n is odd. Similarly, like we have discussed in the previous example, we can also see here that limit of its even term is minus infinity and limit of its odd terms is 0. So we cannot say that the sequence is divergent and it diverges to minus infinity. Yes, the sequence is unbounded below but bounded above. Now, convergence of monotonic sequences. First theorem: every monotonically increasing sequence which is bounded above converges to its least upper bound. That is, if we are given any monotonically increasing sequence and it is upper bounded, okay, if the given sequence is bounded above, then it will converge to its LUB, means least upper bound. Every monotonically decreasing sequence which is bounded below converges to its GLB, means greatest lower bound. If the given sequence is monotonically decreasing and it is bounded below, then it will converge to its GLB. Theorem 2. The necessary and sufficient condition for the convergence of the monotonic sequence is that it is bounded. Okay, if the given sequence is monotonic and also it is bounded, then the sequence will be convergent. Next, every monotonically increasing sequence which is not bounded above diverges to infinity. Consider the sequence n, it is bounded below and also it is monotonically increasing sequence, and we know that the sequence n is divergent and it diverges to plus infinity. Similarly here, every monotonically decreasing sequence which is not bounded below diverges to minus infinity. Here you can consider the sequence minus n, and we know that the minus n sequence is monotonically decreasing and also it is divergent sequence and it will diverge to minus infinity. Next theorem: every monotonic sequence either converges or diverges, or a monotonic sequence is never oscillatory. Why? Just we can understand by having look at the definition of monotonic sequence. Okay, so if you know the definition of monotonic sequence, we can say that the sequence which is monotonic cannot oscillate. Either it will be convergent or it will diverge. Okay, limit point. A real number L is said to be a limit point or a cluster point of a sequence if every neighborhood of L contains infinitely many terms of the sequence. If any real number L, if we have any real number L, and if I am taking a neighborhood at this point L, and if that neighborhood contains infinitely many terms of the sequence, then this point real number L will be the limit point of the sequence. Or second definition, a real number L is said to be a limit point of a sequence n if for a given epsilon greater than 0, for a given positive integer m, there exists a positive integer k greater than m such that ak minus L mod of ak minus L will be less than epsilon, that is this ak will belongs to this interval L minus epsilon and L plus epsilon. Before we move on to our next topic, I want to request that if you have not subscribed the channel, then please subscribe our channel and also hit the bell icon so that you will get the notification of all our new videos. Difference between limit and the limit point of the sequence. We know that a real number L is the limit of the sequence n if for every epsilon greater than 0 there exists a positive integer m such that mod of n minus L is less than epsilon for all n greater than or equal to m, which implies that n will belongs to this interval for all n greater than or equal to m. Now this interval contains all the terms of the sequence except the first m minus 1 terms. Why? Because for the values of n greater than or equal to m, this n will belongs to this interval, so that only m minus 1 terms are left out of this interval. Okay, infinitely many terms of the sequence lie in the interval, this interval, and only finitely many terms lie outside the interval. Thus, the main difference between limit and the limit point is that in the case of limit, the number of terms that lie inside the interval must be infinite, and the number of terms that lie outside the interval must be finite. Okay, you must remember this word finite, that only finite number of elements are left out of this interval. But when we are talking about the limit point, the number of terms lie inside this interval must be infinite, and there is no condition on the number of terms that lie outside the interval. They can be finite, they can be infinite. Okay, if I consider this sequence 1 2 1 2 1 2 and so on, so here we can see that this 1 is also a limit point, 2 is also a limit point of this sequence. Okay, if a term of the sequence appear infinitely many times, then it will be a limit point of the sequence. Now here is 1, here 2. If I am taking a small neighborhood at 1 and also I am taking a small neighborhood at 2, then I can see here that this interval contains infinitely many terms of the sequence, because 1 appears infinitely many times. This interval at 2 contains infinitely many terms of this sequence, because 2 appears infinitely many times. And also the same time I can say that this interval contains infinitely many terms, but infinitely many terms are left outside this interval. Okay, if I am only considering this interval, then it left infinitely many terms outside it. If I am also considering this interval only, then also I can say that if it contains infinitely many terms, then it is also leaving infinitely many terms outside this interval. Okay, now you are getting the point. So in case of limit point, there is only condition on the number of terms lie inside the interval, that must be infinite, but there is no condition on the number of terms that lie outside the interval. They may be finite, they may be infinite. Now remark, the limit of the sequence is also the limit point of the sequence. In fact, if L is the limit of the sequence, then it is the only limit point of the sequence. Now next, limit point may not be the limit point of the sequence. Just I have previously discussed the sequence 1 to 1 to 1 to and so on. You can observe that 1 and 2 are the limit point of the sequence, but they are not the limit of the sequence. Just I have discussed the difference between this limit and limit point of the sequence. Okay, from there you will get the this result clear. Limit point of a sequence may or may not be the term of the sequence. Okay, if I am considering the sequence 1 upon n, then 0 will be the limit point of the sequence, but that 0 will not be, and we know that 0 is not a term of this sequence. Next, if any term of the sequence is repeated infinitely many times, then that term is the limit point of the sequence. Okay, now this result came. For example, the sequence 1 2 3 1 2 3 1 2 3, this has 3 limit points, namely 1 2 and 3. Okay, you can make any number of terms here. If I take 1 2 3 4 1 2 3 4 1 2 3 4, then that 1 2 3 and 4 will be the limit point of the sequence. Okay, then you can construct any sequence. Okay, if you want a sequence with 500 limit points, then you can construct the sequence by taking 1 2 up to 500, and then you have to repeat all the 500 terms infinitely many times. Now let us quickly look at some results on the limit points. Limit point of the range of the set of the sequence is always the limit of the sequence. The converse of this result is not true in general. Consider this sequence 1 2 1 2 1 2. Here it is clearly visible that 1 and 2 are the limit point of this sequence, but in the range set only I have only 1 and 2, and we know that if the set is finite, then it will not have any limit point. You can see here. Next, Bolzanovistra's theorem for sequence and the limit form. Every bounded sequence has at least one limit point. If the sequence is convergent, then we know that convergent sequence has only one limit point. And if the sequence is oscillating, finitely oscillating sequence, then we know that the oscillating sequence has two limit points. So both these sequences are bounded, and this theorem says that every bounded sequence has at least one limit point. An unbounded sequence may or may not have a limit point. For example, consider this sequence n. N is an unbounded sequence and has no limit point. On the other hand, consider this sequence. In this sequence, you can see here that 0 appears infinitely many times, and also this sequence is unbounded, but 0 is the limit point of the sequence. So we cannot say that unbounded sequence will not have a limit point. Just look at this sequence. Unbounded sequence may or may not have the limit point. Next result is, if a sequence has a unique limit point, then it may or may not be convergent. For example, consider this sequence 1 2 1 3 1 4 and so on, and this sequence has 1 as its limit point, but here we can see that this sequence is not convergent. Okay. Next, if a sequence is bounded, and has a unique limit point, then that sequence will be convergent. Okay, you have two possibilities for bounded sequence. One is convergent and one is oscillating finitely sequence, but in both that sequence only convergent sequence has a unique limit point. So this result says that if a sequence is bounded, moreover if it has a unique limit point, then that sequence will be convergent. Next, every bounded sequence which is not convergent has at least two limit points. Okay, so you can consider here a oscillating finitely sequence or a sequence 1 2 3 1 2 3 1 2 3. That sequence will have three limit points. That sequence is bounded, but that sequence is not convergent. The set of limit points of a bounded sequence is bounded. Next, the set of limit points of an unbounded sequence may be or may not be bounded. For example, consider this sequence 1 plus 1 upon 2, 2 plus 1 upon 2, 1 plus 1 upon 3, 2 plus 1 upon 3, 3 plus 1 upon 3, 1 plus 1 upon 4, 2 plus 1 upon 4, 3 plus 1 upon 4, 4 plus 1 upon 4, and so on. And this sequence is unbounded, and the set of limit points is n. How I can see here, we can see here that these numbers 1 plus 1 upon 2, 1 plus 1 upon 3, 1 plus 1 upon 4, these terms are approaching 1, and similarly these terms 2 plus 1 upon 2, 2 plus 1 upon 3, 2 plus 1 upon 4, okay, these terms are approaching 2, and similarly these terms are approaching 3. So the limit point of this sequence will be n, and which is unbounded. On the other hand, consider this sequence 0 1 0 2 0 3 0 4. This sequence is also unbounded, but its limit point is 0 and the set of its limit point is bounded. The set of limit points of a sequence is closed set. Next, the set of limit points of a bounded sequence is a compact set. Next, every bounded sequence has a greatest and the least limit point. If I consider the sequence, any bounded sequence like a minus 1 power n, then minus 1 will be the least limit point and 1 will be the greatest limit point. Or I can consider the sequence 1 2 3 1 2 3 1 2 3 and so on, and in that case 1 will be the least limit point and 3 will be the greatest limit point. Next, let S be any non-empty subset of R and An belongs to S. For all n belongs to n, then every limit point of the sequence An, if any, belongs to S bar. Further, if S is closed set, then every limit point, if any, belongs to S. Next, let S be any non-empty compact subset of R, then every sequence in S has at least one limit point in view of the Bolzanovistra's theorem, and all the limit points of the sequence belongs to S. If I consider any compact subset of R, and if I take and then every sequence in S will have limit point in S. If xn belongs to this closed interval AB, then for all n belongs to n, then all the limit points of the sequence belongs to this interval, closed interval AB. Next, if xn belongs to this open interval AB, for all n belongs to n, then all the limit points of the sequence belongs to closed interval AB. In both these cases, the limit point of the sequence will belongs to the closed interval AB. Now next, if xn belongs to this open interval AB, for all n belongs to n, then the limit point of the sequence xn may or may not belongs to the interval open interval AB. For example, if I consider this sequence 1 upon n, then clearly all the terms of this sequence will lie in this open interval 0 2, but the limit point of the sequence is 0 and 0 does not belongs to this open interval 0 2. Now I am considering another sequence 1 plus 1 upon n. Clearly all the terms will lie in this interval and the limit point of the sequence will be 1 and 1 belongs to this open interval 0 3. So if I have any sequence which belongs to any open interval AB, then its limit point may or may not belong to that open interval AB. Range set of the sequence is always countable. Next, if a range set of a sequence is finite, it has at least one limit point of the sequence. Next, if the range of the sequence is infinite, then it may or may not have the limit point of the sequence. Consider this sequence 1 2 1 3 1 4 1 5 and the range set of the sequence is 1 2 3 4 5. Here we can see that 1 is the limit point of the sequence and it also belongs to the range set of the sequence. But if I am considering this sequence 1 1 upon 2 1 upon 3 1 upon 4, then 0 will be the limit point of this sequence, and we can clearly see here that 0 will not belong to the range set of this sequence. So if the range set of the sequence is infinite, then the limit point of the sequence may or may not belong to the range of the sequence. Next, a sequence may have uncountable limit points. For example, if I am considering this sequence sin n, and we know that the values of this sine function lie in this interval, closed interval -1 to 1, and also we know that there are uncountable number of points in this closed interval, and we also know that sine assumes each and every values between this -1 and 1, and also every point will be the limit point of this sequence sin n. Next, let's have a look on some results on null sequences. First, a sequence an converges to L if and only if the sequence an minus L is a null sequence. Next, if an is a sequence, then an tends to 0 if and only if mod of an tends to 0. If an and bn are both null sequences, then an plus bn, the sequence an plus bn is a null sequence. You can consider here 1 upon n and 1 upon n square. Both the sequences are null sequence, and the addition and their addition will be a null sequence also. If n is a bounded sequence and bn is a null sequence, then an into bn is a null sequence. Fifth, if an is a null sequence and k is a constant, then k into n is a null sequence. So we have discussed in this lecture some results on convergent sequence and monotonic sequence. After that, we have discussed difference between limit and the limit point of the sequence, and at the end of the lecture we have seen some results on the limit points of the sequence and few results on null sequences. Now in the next lecture we will discuss some problems on sequences. Thank you.